Hi everyone, I'm going to start taking a look at aqueous solutions. Now it's week 4, it's Wednesday of week 4. I'm going to send out your midterm exam tomorrow. So in the order of operations, probably save this one until after your exam. Okay, so do your exam. This stuff is not going to be on your exam, so save it till after the exam. Kind of review for that, okay, from now, which is Wednesday, you know, take a look at your stuff, take care of that. And then if you've done that HCl titration lab, fantastic, okay, but I did talk about something new in there, which was concentration, okay. Now if you're struggling a little bit with concentration, maybe do this packet first, because literally in the first couple of pages here we're going to talk about concentration and how you work it out. But if you were able to get by with you know, the pre-lab version, feel free just do that first, okay. So I'll kind of set the deadline for this one and the lab to be kind of similar time, okay, so you can kind of work on them both together because they have kind of similar material. All right, so aqueous solution is one of my favorite words. Aqueous is literally from Latin, which means with water, right? So an aqueous solution means you've got stuff dissolved, okay? So sugar dissolves in water, as does salt, so many things dissolve, and that's key because chemical reactions only occur when atoms and molecules can actually bump into each other and stick. So chemical reactions will typically occur in the gas phase where molecules bump and stick, or in solution when they bump and stick. You know, put two solids together, they don't react, right? Liquids, sometimes, okay, but typically you have to dissolve in water. All right, now, in order to get a good handle on what concentration really is, it's good to think about it in terms of the strength of a drink, right? Like an alcoholic drink. So it's an analogy, right? So it's fictitious, right? So let's pretend. When you finish this class, chances are good you'll head out to a local bar for a well-deserved adult beverage, right? So, you know, let's pretend it's the regular semester, chemistry final day. Heroes and legends know that, so they run a drink special for chemists, right? Okay, so you're either in the bar because you're really happy or really sad. Either way, you're going to drink a lot of alcohol. All right, so now here's the kind of hypothetical situation, okay? Let's say you can choose for the same price either a pint of beer or a pint of wine. Which gets you where you want to go better, right? Okay, so the idea is, I guess, to get drunk, right? So which has more alcohol, a pint of beer or a pint of wine? Notice I'm doing a volume per volume analysis, right? So beer is literally 5% alcohol by volume. Check the bottle, right? Okay, wine is 15%. There's 3 times as much alcohol, yeah? So we're familiar with the strength of drinks in terms of percent alcohol. Beer is 5%, right? So 5 out of every 100 milliliters is alcohol. Wine, 15, okay? And we say the wine is a stronger drink, right? Stronger drink, okay? Now in chemistry, stronger equals more concentrated, okay? Concentration in chemistry is the strength of a drink or a strength of a solution. So the solution strength is how many moles of stuff are swimming around in a fixed volume, okay? In simple terms, concentration is how much stuff in how much space, yeah? Okay? So you can have percent volume, that's a concentration term. Chemists love moles, right? So how many molecules, essentially, how many moles of molecules in a certain amount of space, and that space is always 1 liter. Okay, so think of a liter of orange juice. How many moles of sugar are swimming around in the orange juice? That would be the strength of the sugar solution. Okay, so concentration. Now you may have picked this up from the lab you just did. Okay, the units are moles per liter, right? So it's moles of solute, so that would be sugar, for example, or salt, so the stuff you dissolve, per liter of final mixture, per liter of solution, right? So how much salt's in the seawater, all right, or how much sugar's in the Pepsi, right? So it's that final solution, okay? So the moles per liter sometimes is just called big M. Now don't be confused, there are 26 letters and 300 symbols in chemistry, right? So uppercase regular M is molarity, moles per liter strength. You may see on, for example, you know, HCl 2M in the lab, right? So that's a bottle of HCl that's 2 moles per liter strength. Not to be confused with italicized M, which is molecular weight. So I know it's a little bit confusing. There's 2 M's, italicized or bold. Bold is strength, molarity, that's the word we use. Big M, bold. Italicized is moles per liter. Okay, so molarity, Big M is how many moles of solute per litre of solution. All right, the units are moles per litre or just M. Now here's the thing, here's a little phrase we love in chemistry, right? To prepare a solution, you dissolve a solute in a solvent. So for example, say I'm making a, move my little thing back here. Say, oh, have to excuse me a second. There you go, technical issues. So let's assume we're making some Pepsi, which is a solution. What is Pepsi made from? Well, you take some sugar essentially, and it's a multi-solute solution, so sugar, flavor, color, right? And you add it to essentially water. You dissolve a solute in a solution. Sorry, let's say that again. You dissolve a solute in a solvent to make a solution. Okay, so Pepsi is basically a sugar water solution. Yeah, there's other things, but mostly sugar water, right? Can you think of any other solutions? So about vodka, what's that? Vodka is basically alcohol. Oh, move it up so you can see it. Alcohol plus water. Dissolve some alcohol in water, you make vodka, you know. The more alcohol you put in, the stronger the drink. Right. Okay, so that's the idea of solutions. You dissolve a solute in a solvent to make a solution. The solvent's almost always water. Many, many things dissolve in water. It's like the universal solvent, we call it. Okay, dissolves everything. All right, now, in lab, we haven't had that much experience with this, but should you have done lab this semester, you may have made a stock solution. I think in that last HCl lab, they asked you to make a stock solution. Okay, so you need a stock solution. A stock solution is just a solution of known concentration. Okay, so if I want a 1 mole per litre solution, what does that mean? It means 1 mole is swimming around in 1 litre total volume. Yeah, so this is where we have these special volumetric flasks. Maybe you've seen them. Maybe if I can find a nice picture, I'll flash it up on the screen. But you have a flask that's exactly 1 volume, and there's a line here. See the line here? Okay, it's a special shape for a reason. If you think about it, most of the volume is down here, and then as I fill up the neck part, which is really narrow, a small volume is a big height difference. So if you get it right on the line, which is 1 litre exactly, that's the 1 litre line. Okay, the volume of the solution is exactly 1 litre. It's called making it up to the mark, right? So how do we make a 1 mole per litre sodium chloride solution? Well, we weigh out 1 mole, 58.45 grams or whatever it is, you know, molecular weight. Weigh out 1 mole of solid NaCl. It's very similar to what you did with your KHP, right? You weighed out a certain number of moles of that, right? Okay, so 1 mole of NaCl, in it goes, right? It makes a little pile in the bottom. Then typically in real life, you fill it up to about here, and then you swish it around, right? And it all dissolves. Then you fill it up to the line, make it up to the mark, switch it around some more, and then you have your exactly 1 mole per litre strength, or 1 molar, right, HCl, or NaCl in this case. Okay, 1.0 M, 1.0, move it up, mole per litre. Okay, so that's how you make a solution. All right, you put a mole in a beaker, or a flask in this case, make it up to the litre line. 1 mole swimming around in a litre. If you want 2 moles per litre, put 2 moles in there. You want half a mole per litre, put half a mole in there. Okay. All right, now, if this was class, we'd have a very kind of interesting demo. I'd actually make this in front of you. I'd actually open a bag of sugar in front of you, pour it into a container, add some water, and do the whole thing. Okay, but we've got to kind of do a thought experiment here. So, what's the concentration of a solution made by dissolving 2.845 grams of sugar, so that's a pack of sugar, right, one of those little packs of sugar, and making the final volume 150 milliliters. Now here's the thing, I talked about it a little bit in your pre-lab earlier, right? Moles, as we see in just a few minutes, is really the central kind of clearinghouse of all chemical conversions, right? So if we think about solids, when we're thinking about solids, right, you got molecular weight, grams and moles. We talked about that. You weigh something on the balance, use its molecular weight, and you can get its moles, right? Fair enough. But if I have an aqueous, and we did this in the pre-lab, right? What's that? Well, moles is concentration. Sorry, concentration is moles over volume in liters. Okay, and that's the other triangle. What connects the two is moles. So you can weigh something, put it in a flask, make it a certain volume and find its strength. And that's exactly what we're going to do with the sugar solution, okay? So let's read the question and then kind of use this one, then this one, okay? So what's the concentration made by dissolving 2.845 grams of sugar, so in some water, making the final volume 150. So what we're going to do, we'll put in 2.845 grams of C6H12O6. Now, to be honest, rather than do a chain conversion for these, I kind of like to kind of do them separate, because concentrations is a little tricky when you try and do a chain, okay? So I'm going to kind of keep the Hatfields and McCoys apart a little bit, right? So the first thing I'm going to do, I'm going to find the moles of sugar. And we did this before, if you remember, one of those worked examples, right? So moles is grams over molecular weight. Moles equals grams over molecular weight. Grams was 2.845 grams. Molecular weight, if you flip back, you can find out it was 180.2 grams per mole. And what do we get? Make sure you get the same thing I do, 0.0158 moles. Fair enough, right? So we've got 0.0158 moles of just solid sugar sitting in the bottom of that flask, right? Fair enough. And then what we're going to do, going to keep this separate here, make that up to 150 milliliters, stir it around, dissolve it. So now it's all dissolved, right? So now I have my sugar water, right? What's the strength of the sugar water? Well, if you think about it, I didn't add sugar to this beaker when I put water in it, right? So that amount of sugar is fixed, 0.0158 moles, and it's now swimming around in this volume, right? Fair enough. So the moles is fixed. The moles between the two is fixed, okay? But now, what do we want? We want the strength, right? So concentration is moles per volume, right? Concentration, moles over volume. But the volume has to be in liters. Now I'm going to do the conversion on the fly. Hopefully you know 150 milliliters is 0.150 liters, right? So the same number of moles, 0.0158 moles over 0.150 liters. Moles per liter is the unit. Remember, units are super, super important, right? And that equals 0.105 m, or 0.105 moles per liter. This is interchangeable units. You can use either one. Molarity, moles per liter, same thing. Okay, so if you think about it, I planned my journey. I weighed my sugar, allowed me to get moles using molecular weight. Then, once I got the moles swimming around, I knew the volume of the final solution, I could figure its concentration. Okay, so that's, if you like, in a certain direction. I could go the other way, right? And in class, for the first 5 people that actually work out this question, I give them extra credit. So that's what I'm going to do for you guys, right? So if you can get this, to me, let's be super generous, right? I'm going to go before Monday, right? So 11:59 Sunday night. Before Monday, if you can get this to me before Monday, what mass of NaCl is contained within 0.5 liters of 6 moles per liter solution? Okay, so you're going to start with concentration and volume. Concentration times volume equals moles, right? Once you got moles, you can use molecular weight to figure out the grams. Okay? All right, hopefully that will work for you. Okay. Again, you know, usual thing. Email, make it plus just 1 point, right? It's just practice. All right, now, here's an important one, right? So, typically, when we have an aqueous reagent, so maybe something dissolved like sugar or salt or whatever it is, or maybe acid like HCl, right? We can't weigh the acid in the solution. It's 99% water, so weighing a solution is pointless because you're just weighing the water mostly, right? So you can't weigh a solution, so you have to use concentration and volume whenever you see aqueous, right? So back here, that's kind of a subtle point. Whenever you've got an aqueous state symbol, use concentration moles per liter. Whenever you've got a solid, typically weigh that on a balance, right? Moles, grams, molecular weight. Okay, so whenever we see aqueous, we should probably use moles as concentration times volume, right? Just like we did in the recent lab, okay? Now, let's go back and kind of look for real at my favorite example, right? So there's our trick, since moles equals CV, right? So concentration, let's go here. Concentration is moles per volume, and that's in liters. So the most common version of that is moles is CV, and that's what we used on our lab, right? Okay, so if you think about that, I could put that into slides and ladders, no problems. And so instead of grams, molecular weight, and moles, I could have concentration times volume equals moles. Trick, right? So here we go. So what volume in milliliters of 2 moles per liter HCl, and that's stuff you would actually use in a lab, right, is needed to completely react 5.5 grams of chalk. So before, when we did that, how much HCl did we need situation with the 5-gram stick of chalk? That was kind of just for fun, right? Just for practice. In the real life situation, you would not figure out what mass of HCl in a solution. You'd figure out the concentration volume is moles kind of thing, right? So let's do it. So here's my favorite. That's aqueous, that's solid. Grams molecular weight moles for solids. Concentration volume equals moles for aqueous. Okay, so let's read this one. All right. First up, I'm going to set up a blank grid, right? So I'm going to not label it. I'll do a grid though, right? So there's my grid. What volume, and it wants milliliters, 2 moles per liter strength HCl is needed to react 5.5 grams of chalk, right? So there's my grams, my molecular weight, and my moles as normal for the solid, right? If you remember, chalk was 100 grams per mole. 5.5 grams. It says what volume. Now here's the thing. Concentration times volume is moles for an aqueous, right? So that times that equals that. We divide to go down. Grams divided by molecular weight is moles for a solid. Concentration times volume equals moles for a solution. Okay, so I've modified the grid to take care of this aqueous, right? Then we can just finish putting stuff in. It says 2m strength, right? That's concentration. We can put 2.0 m, or if we like units better, moles per liter. Volume's what we got to find, right? Okay, so we've got to find volume. So our journey is this, right? We can figure out, this is a 1:2 ratio, we can figure out how many moles of calcium carbonate we have, multiply by 2 to get here, then we have 2 from the 3 things in our triangle. We can just kind of work it out on the side maybe. Okay, so if you want to pause there and give it a shot, do that. Come on back, I'll show you how I got it. Okay, so divide to go down. 5.5 grams is 0.055 moles. So that means double that from here to here. 1 needs 2, so 0.11 moles. 0.110 moles, okay. Now, I can't, I'm not going up to the top here, so it's no kind of simple multiplying or dividing, go up or down. I've got to rearrange my triangle, all right? Triangle volume is moles over concentration, okay? So volume equals moles over concentration. This is what they were kind of alluding to in the pivot video, okay? Because this is not a 1:1 ratio, so you need to do a slides and ladders because there's a factor of 2 here, right? CV does not equal CV in this case. If it was 1 and 1, it would, like the lab, but here it's 1 and 2, so it'd be off by a factor of 2. Okay, put the numbers in. 0.110 moles, is that one, divided by 2.0 moles per liter. Oh look, moles cancel, we're left with liters. Figure it out, how many liters is that? 0.055 liters. Careful, if this were a conversion problem, like on a quiz or a test, yes, I'd want you to show this step as part of the conversion, but everybody knows 0.55 liters is 55 milliliters, right? Okay. All right. Now then, are we done? Not quite. It also says what volume is CO2. If we look here, 1 reacts with 2 to make 1, 1, and 1, so I'm going to have 0.055 moles here. Real quick on the side, 0.055 moles CO2 times STP, of course, 1 mole, 22.4 liters. What do I get? 1.23 liters. Okay. All right. Maybe it's kind of there. There we go. Hopefully that makes sense. Okay, so that's a big time slides and ladders. That has everything in it, right? So it has all the tricks, everything. It has aqueous, has balancing, has, sliding, 1 to 2. Okay, the only thing it didn't have was a limiting reagent. All right, now then, one thing they talk about a little bit in the book, and I don't think they talk about it so well, is dilutions. Okay, so this is something you actually have a lot of experience with, particularly if you like coffees, right? So think about an espresso coffee versus a cafe Americano, right? In an espresso coffee, you have this little tiny cup with this very strong coffee in it, right? Okay, and then if you make a cafe Americano, you take that espresso shot, put it in there, and then make it up with water, right? Here's the question: which one of those has the most caffeine in? You're thinking, oh, the first one, because it tastes so strong. Well, no, because if you think about it, I had maybe, I represent it by 5 dots. I have a certain number of caffeine molecules in this small space in the espresso, and then I put them in this big space and just make up the difference with water, right? So it's the same number of molecules swimming around. So the moles in this one equals the moles in that one. So when you dilute something, the moles doesn't change. But what does change? The volume, right? So we know that moles equals CV, right? So if you like, when the volume goes up to equal the same number of moles, the concentration goes down. That's why a cafe Americano tastes weaker than an espresso, right? Because it's diluted, right? It's more volume, okay? The strength goes down, the volume goes up. It's kind of a, what we call a synergic effect. They go in opposite directions, okay? So if we think about that, moles before equals moles afterwards, so CV before equals CV afterwards, right? And that's what we got down here, right? So concentration times volume before you dilute equals concentration times volume after you dilute, right? So if the volume goes up, just like in our espresso example, the concentration goes down. And it kind of also works the other way, right? It kind of works the other way. Now, I've been married for 20 years, right? And I've learned a trick or two, right? I can now do rudimentary cooking, right? If you ever made a pan sauce, how'd you do that, right? So you get your, cook your chicken or whatever, right? And you get all these little, what Emerald calls yum-yums, little kind of caramelized kind of meat chunks in the bottom, right? All the tasty little crumbs, right? And what you do, you throw in some alcohol, usually some wine, and you deglaze the pan so that dissolves off, and then you put some chicken stock in there, right? And that's like soup at that point, yeah? Okay, so that has a certain concentration and a certain volume, right? Which is a certain number of moles of flavor molecules, right? And what you do, you heat this up, right? And what happens? Well, the water evaporates, right? So the volume goes down. What happens to the concentration? What happens to the flavor? It goes up, okay? So if you evaporate off water from a solution, you'll make it stronger. Makes sense, right? Okay, so bottom line is concentration times volume before equals concentration times volume afterwards. If I dilute or if I reduce, doesn't matter. I just change the amount of solvent. Up or down, that changes the volume up or down. Okay, so here's a question for you. So I'll give you guys a moment to try it and then I'll go through it. Okay, so let's just read it. So oh, sorry, I'm just looking at the time here, 23 minutes, okay. So if we look at the question, we're going to make a standard solution, yeah? So in a laboratory procedure, it requires you to make 100 milliliters of 2 moles per liter strength solution from an 18 moles per liter stock. Now, we don't buy giant bottles of 0.1 moles per liter acid to the mail, because that's silly, it's mostly water. It's a bit like orange juice, right? So most people buy orange juice in the frozen concentrated form. So this tiny little container of frozen concentrated orange juice comes to your house via the supermarket. You put it in a pitcher, you make it up to a larger volume, and then you got your orange juice, right? So you don't send, liters of water around the country. You just waste money with fuel and stuff, right? And that's what we do with chemicals. So we buy really concentrated stock solutions and then just dilute them down to what we want, right? This is a great example of making a stock, right? So if we read it, a procedure requires you to make 100 milliliters. So our final volume is going to be 100 milliliters, right? Of 2 moles per liter strength, right? So what I like to do is this, right? So C1, V1, C2, V2. Now, if I was going through moles, I would, use liters, but because I'm going to cancel milliliters, I can use them, okay? So I'm going to use volume 1, well, we don't know what that is, right? Volume 2, we know we want 100 milliliters of 2.0 molar, right? The initial concentration is 18, so that's kind of the strong stuff, right? Okay, so what we're going to do, if I draw a picture, we're going to put a little bit of 18 moles per liter in there, and then add water to make it up to 150 milliliters, okay? And we want that final solution to be 2 moles per liter. Well, think about that, yeah? So because C1V1 equals C2V2, and we want volume 1, the amount we start with, to make it up to the line, right? We're solving for V1. So V1 equals C2V2, oh, move it up so you can see it, over C1, which equals 18 moles per liter, 150 milliliters, over concentration, oh sorry, concentration 2 was 2.0 molar, 18 molar, yeah, 2 and 1. Okay, work it out. What you get? 0.11 liters or 11 milliliters. So I start with 11 milliliters and I make it up to 150. That turns my 18 of 11 into 150 of 2. Okay, so I've diluted. Okay, all right. Now, just enough time to show you this super important slide, okay, and then we'll take a quick break before we continue. Okay, so we now have the 4 conversions that go to and from moles, all right? And I call this the spider diagram because it kind of looks like a spider, right? So this will allow you to plan any journey, any conversion that involves moles, right? So what I'm going to do to help you remember, that's my spider, right? And this is body anyway, right? Now spiders usually have 8 legs. This one's been in an accident. It only has 4 legs, right? So draw that, right? Now, you know, just from the last packet or two, what you can convert moles to and from. And we've just done the last of those, which was concentration, okay? So, probably the classic, moles to grams, right? You weigh stuff on the balance, grams of a pure substance. Anything with a formula. Use molecular weight, or if it's just atoms, periodic table, right? Okay? Use molecular weight, grams, and moles. We did a lot of those previous packet. Okay? So I can go from a grams to a moles. If you did that example with the salt water, this is one of the legs of the journey, right? Okay. Now, go from grams to moles. If you think about our early examples, we went from grams to moles, and then I said, oh, well, Avogadro number, right? We can actually work out the number of particles. Avogadro number, 1 mole, 6.02 times 10 to the 23 particles. So you said, for example, we had 12 grams of carbon, which was 1 mole, which was 6 times 10 to the 23 atoms of carbon. Okay. All right. So those are the 2 first ones we did. And then we did, now you've got to be careful here, right? We did volume of a gas at STP. Now students always make this mistake. It's gas, right? That's the state symbol. Maybe I'll put state symbols on these. Grams usually a solid. Gas, 1 mole is 22.4 liters, okay? That's Avogadro gas law. Same guy. Busy, right? Okay. Students, when we talk about concentration, which is moles per liter, they get the volume mixed up, right? So liters is the same unit each time, but it's liters for a gas. 22.4 is 1 mole. When we talk about concentration, volume of a solution, that's aqueous, right? So if it's got the aqueous symbol, it's concentration moles per volume in liters. If it's aqueous. If it's a gas, it's 1 mole is 22.4 liters. These are not doing the same thing, of course, right? Okay. So if we think about our previous couple of examples, right? So from grams to moles, moles to concentration and volume. If you did that sodium chloride one, I gave you, concentration and volume here, which allows you to do moles. If you didn't quite get that one, go back now, right? Because I've just given you the journey, yeah? So concentration times volume is moles. And hey, moles, molecular weight in grams. You can find grams. Okay, so let's pause there, and we come right back and talk about electrolytes. Okay, so next on our list of things is electrolytes. Okay, maybe you've heard that phrase before, electrolytic solution. Turns out Gatorade is an electrolytic solution. Okay, interesting. What's special about Gatorade? Why is it so famous? Well, back in the day, University of Florida, they decided, hey, people don't sweat water, do they? You can try that experiment. Next time you work out, quick experiment, taste. You taste salty, right? Because you don't sweat water, you sweat salt water, okay? And the dissolved salt is what's known as an electrolyte. So a dissolved ionic compound is an electrolytic solution. Okay, so what Gatorade did was they just put salt in some sugar water, and it made athletes recover more quickly because you regain the stuff you lost through exercise, right? Okay, now electrolytic solutions get their name because they conduct electricity. Why do they conduct electricity? Because they contain separate mobile ions, okay? And I'll introduce a video, okay, in a moment, okay, and it will show you this kind of process in action. But bottom line is this, okay, turns out that water, if I do a little picture of water, we'll talk about this in more detail later, but it turns out that water, oxygen is a bit of an electron stealer, hydrogen is not. So this end of the molecule is a little bit minus, that end's a little bit plus, right? This is what's called an electric dipole. So think of water of having a plus end and a minus end, yeah? And this is my favorite analogy. I actually grew up in a small farming community, believe it or not, right in the middle of nowhere. And tractors are kind of cool things. And we used to, you know, work on the farm and drive the tractors around. And tractors are cool because they kind of remind me of water, because a tractor can hook stuff up on the back and it can hook stuff up on the front. You can put a plow on the back and pick up a hay bale on the front, right? Okay, so tractors can hook up on the back or hook up on the front. So can water, right? So the minus end sticks to plus things and the plus end sticks to minus things. So if we look here, there's a water molecule and it's the plus end there, essentially hooking up to a minus ion and then dragging it off into solution. Okay, so imagine a water molecule backing in, hooking up to an ion, taking it into solution. It can go in backwards or it can go in front first, right? Okay, and the bottom line is you get these layers of water around ions. Okay, so each bond is actually quite weak here. Yeah, each bond is quite weak, but there are like maybe 20 small bonds, right? So it turns out that the ions are more strongly stuck to the water than they are to each other. That's why things fundamentally dissolve, okay? A bunch of tiny strength bonds outweighs maybe 4, 5, 6, whatever it is, strong ionic bonds, right? So ionic compounds that dissolve, the ions stick more strongly to the water than they do themselves. Okay, these are called, if this was NaCl, that would be the Cl minus aqueous ion. Aqueous, there's the aqueous, right? Those layers of water, right? This will be an Na plus aqueous. So there they are, separate mobile ions in solution, okay, are electrolytes. They can move if they're pulled by a voltage, okay, charges will move if pushed by a voltage, it will conduct electricity, hence the origin of the name electrolyte. Okay, so let's pause for the video, come back. All right. All right, how did you enjoy that video? Okay, so the bottom line is, if we just kind of turn the picture into words, I've got NaCl, right? So you may be putting some salt in your pasta or whatever, right? The water, yeah? Okay, so the little salt crystal, there it is. It's NaCl, NaCl, right? NaCl solid, that's its chemical formula, right? When it dissolves, it breaks up into separate mobile ions. So we can actually, even though we write that as NaCl aqueous, that's kind of a lie, right? Because in reality, it's two separate mobile ions. We'll just do that for shorthand, okay? So whenever you see an ionic compound written aqueous, remember, it's actually broken up into its component ions, okay? All right, so that's an electrolytic solution, okay? Now we need to know about dissociation, which is the breaking apart of ions in solution, in order to kind of understand how these things work correctly, okay? All right, now, talking of which, right? So I mentioned a couple of packets ago that we'd come back to the double replacement reactions in some detail. And here we are, okay? It turns out there's three ways you can actually write equations for double replacements, okay? There's the balance, which we've already learned, which is the most common way, okay? And then the complete, which is breaking them up into their separate mobile ions, which is actually how it really is. And then we can actually do a little neat trick and make a net, which is like a summary, okay? So balanced ionic equation is simply a double replacement, swap the partners, remember Austin Powers, right? It's a reaction you're already familiar with, okay? So let's do this one. Silver nitrate and sodium chloride solutions. So this one we already did. It's a nice easy one to start. There's sodium nitrate solution, +1 -1, correct formula, plus sodium chloride, +1 -1, correct formula. Swap partners. Now there's going to be no balancing numbers because they're all +1 -1. Okay, we're going to get AgCl plus NaNO3. Fair enough, right? However, now we have a problem because it turns out that one of these products will be a solid, right? And one of them will be an aqueous. But how on earth do we know? That's the $64,000 question. In the past, I've kind of told you, right? This one is actually going to be the solid, and this is going to be the aqueous. But from now on, we've got to figure that out, right? And it's a super important point because we can't go to steps 2 and 3 unless we get these state symbols assigned correctly. All right, so let's talk about how we assign state symbols to products, all right? So whether or not something's a solid or an aqueous, its solubility, that information can be determined by looking at a chart, right? It's called the solubility chart, shocker, right? Okay, so show you the solubility chart. Now it's best if I just cover up one side, okay? It's like a glass half empty, glass half full situation, all right? Now, if we look here, it says soluble compounds, right? Things that dissolve will have typically the aqueous state symbol, right? Not typically, all the time, right? So things that dissolve, aqueous, they're stuck to water, right? And it's done in terms of what's the anion, what's on the back, right? So anything with nitrate on it, chloride, bromide, iodide, or sulfate, any of those things generally will dissolve, right? In fact, if it's nitrate, it's a no-brainer because every single nitrate compound dissolves. If we just go look up here real quick, if I can kind of get both on this chart at the same time, there's silver nitrate, right? And it's aqueous because all nitrate compounds dissolve. Over here, we assign sodium nitrate as aqueous, and now I know why, because all nitrates dissolve, no exceptions. This is a list of things that are exceptions, right? No exceptions. Fair enough. Now, these guys, if we look at our periodic table, chlorine, bromine, iodine as ions, chloride, bromide, iodide, they're in the same group, right? Things in the same group typically have the same chemistry, and that runs true for these guys, particularly with solubility, okay? So the halides, they're called, generally dissolve. They're in the solubility camp, right? However, there are 3 exceptions. So silver chloride, mercury chloride, or mercury 2 chloride, and lead 2 chloride. Silver, mercury, and lead chlorides are exceptions, so they'd be solids. All right, so let's look up here, look. NaCl, well, we know sodium chloride dissolves. We make pasta all the time, right? That's because sodium is not an exception, so it dissolves, right? But look, there's silver. Silver's a solid. Ah, silver's an exception, okay. Sulfate, somewhat similar, apart from barium and silver are switched out. Okay, now if I kept going and I looked at other ions like phosphates and hydroxides and things like that, the number of things that made solids, the number of exceptions would grow. And it would grow so much that it would get unwieldy, right? So instead of the glass being half full, we kind of look over here at the glass being half empty. So generally speaking, these things are insoluble. These are solids. So generally speaking, carbonates, phosphates, and hydroxides are solids. Calcium phosphate is bone. That doesn't dissolve. Chalk is calcium carbonate. That doesn't dissolve, right? Okay, so generally speaking, carbonates, phosphates, and hydroxides, compounds with those anions on the back, are solid generally. However, there are a few exceptions, right? So carbonates, ammonium and group 1A cations, right? That means not just +1, but anything only from this column. This is group 1, remember, okay? So hydrogen, get it right. Hydrogen carbonate, lithium carbonate, sodium carbonate, potassium carbonate would all dissolve because they're exceptions to this rule, okay? All right. Sodium hydrogen carbonate is baking powder. That dissolves really well. Okay, so similar rule for phosphates. Hydrogen phosphate is just phosphoric acid. That dissolves really well. Hydrogen carbonate is carbonic acid. That dissolves really well. All right. Hydroxide is kind of a mixed bag. Okay, it's kind of weird. If we look here, strontium and barium actually appear in group 2. There they are. But calcium and magnesium are not on the list, right? Also, calcium, strontium, and barium on the list, but magnesium is not, which is really weird because we get a break in group chemistry, right? So if we just look at that, generally speaking, hydroxides are solids, all right? So magnesium hydroxide would be a solid, but calcium, strontium, and barium hydroxide would be aqueous, which is interesting. Okay, so we use this chart, and it will be always on the data sheet. You may have seen it on the last quiz, actually. I just throw it in there, right? Okay, so this solubility chart always available to you, okay? Just know how to use it, and that's kind of where we're going now. So maybe I'll do a thing here, so I got the room. All right, I'll do this. Have your chart ready, okay? So there's your chart and there's some questions, right? So use the chart and state whether the following are soluble or insoluble. Just put a state symbol next to the formula, okay? If you feel confident, do it. If you want to maybe watch me do a couple and then do a few, fine, right? Okay. So first one, sodium nitrate, no-brainer. All nitrates are soluble. AgCl, just did that one a minute ago. Chlorides generally are soluble. Oh, but wait. It's an exception, so that's a solid, just like our first equation. PbCl2, whilst chlorides generally are aqueous, oh, but wait, it's an exception again. Ah, tricky. Calcium hydroxide, generally hydroxides are solids, but wait, calcium is an exception, so that's aqueous. Lead sulfate, sulfates generally dissolve, lead's an exception. I do a lot of exceptions today. Finally, silver hydroxide. Now be careful with this one, because hydroxide, group 1 plus 1 cations are exceptions, but silver, not in group 1. It's a transition, right? So there it is. Oh, there it is. So that one is not an exception, so that's a solid. Okay. All right. Hopefully that made sense. Okay, I'll keep that on the side for future use. All right. So bottom line is, write your equation in the typical way we learn. Okay, so write a balanced chemical equation. Then to the products, you can now, using the chart, assign state symbols. And that's super important when we go on to the next version, which is the complete ionic equation. Okay. Now remember that if we see something with NaCl aqueous, for example, there's actually 2 ions separate moving around in solution. So we've got to express that like it really is. Okay. So the complete equation just splits formulas up, which are aqueous and ionic. Okay, so if you think about it, how did you make AgNO3? If I said to you, how do you make silver nitrate? Well, +1, -1, bring them together, AgNO3. If I just took them apart, Ag plus, NO3 minus. It's just the reverse process, right? Okay, so the math you use to put them together, do it in reverse to take them apart, right? So I like to think about it like this. I've got a balanced equation here, all right? And if you do the first couple, draw pictures, right? So if I've got AgNO3, there's one Ag and one NO3, right? So if I split it up, so I've got Ag plus stuck to NO3 minus. If I split it apart, what do I get? Ag plus, aqueous, and NO3 minus. aqueous. That's what I get when I break it apart. Just do that math backwards. If I said to you, what's the formula of silver nitrate? These are the ions you stick together to make that, right? Okay. Plus, what have I got here? NaCl, right? Well, what's NaCl made from? Na plus aqueous plus Cl minus aqueous. All right, so I'm drawing a little picture down here. When I squirt these two reactants into a beaker, I got Ag plus swimming around, I got NO3 minus swimming around, I've got Na plus, Ag plus, NO3 minus, Na plus, and Cl minus swimming around. Now, do you remember my rather dodgy analogy for this? This is the swinger reaction, right? Okay, so here they all are, mingling at the party, right? Okay. Ag bumps into NO3. Oh, see you later. Ag bumps into Na. Oh, sorry, dude. Get it? All right. Ag bumps into Cl. Hey, baby. Ag and Cl hook up. They make the solid. So that's not written split apart. There they are, right? If this was real life, you'd be tweeting this immediately, right? Okay. But what about the other pair, right? Aqueous. That means they did not hook up. So Ag bumps into NO3. See you later. Na bumps into Cl. See you later. Na bumps into Ag. Sorry, dude. Na bumps into NO3. You know what? You're not my type. You'll always find me in the kitchen at parties, right? They do not get together because they remain as separate mobile ions. So at the end of the day, we got a pile of AgCl. We'd actually see a white powder or precipitate form, and we have these ions just sitting up here kind of watching. And spookily, that's what they're called. They're called spectator ions because they just watch the action go on, right? Okay. Now, important, okay? Only aqueous can be written separate, okay? Typically solids are the other state, but liquids and gases too could not be written separate, okay? All right, so that's the longhand version. That's the longhand version, all right, the complete. All right, now, if you were texting what happened at this party, Ag hooked up with Cl, right? You got 120 characters or whatever, you're going to tweet it out, right? So when you look at this, you can actually summarize where the action is. It's called the net ionic equation, okay? And very simply, all I'm going to do is a little bit of algebra, right? So if I look, think about algebra for a second. What is it? So you can cancel things both sides of an equation that are identical. So if I see two things, doesn't matter if they're chemical formulas or numbers, two things both sides the same, I can cancel. And it turns out the phrase in the book is cancel spectator ions. So Na plus is the same both sides. It didn't change. It was just watching. So is NO3. And what I'm left with is where the action is. It's kind of common sense. What did I make? AgCl. How did I make it? Ag plus hooked up with Cl minus, right? So you can just go straight, you know, you can skip the cancelling and just go straight to common sense if you like, as long as you write the answer, right? State symbols are super important. Now, you wouldn't have got that if you had signed AgCl as aqueous, right, in the first step. So assigning state symbols, super important. So the book says, and I kind of like the phrase, you know, cancel spectator ions to get the net. Okay, all right. Now, that was an easy example because it was 1, 1, 1, 1 with the stoichiometry, right? Here, we have something with non-similar balancing numbers, okay? So what I want you to do, if you feel confident, try it, right? If you feel confident, try it, but I'll go through it nice and slow, okay? So first things first, and I'm not going to give you the products because we know they're going to swap partners, right? So think about the name in your head, names to formulas, first step, right? So I'm going to get lead iodide. Lead is a +2, so I need 2 minus 1s. Okay. Then potassium +1, nitrate -1. Names two formulas, right? Names two formulas. Those are the correct formulas. +2 minus 1, need two of them. +1 minus 1, 1-to-1 ratio. Okay. Now we can put numbers in front to satisfy your screaming brain, right? Because there's only one iodide there and there's two there, right? So because it's ionic, just count the ions. Consider the nitrate a bag of atoms, right? Just count the bags. So maybe let's do nitrate first. So I got 1 nitrate bag here and 2 there. So I need 2, all right? If I draw this, I got K plus NO3 minus, and then another K plus NO3 minus. So that's 2K NO3, right? So that's my nitrates balance, all right? Let's just check lead. 1 lead there, 1 lead there. That's good, all right? Now I've got 2 Ks, 1 K there, 2, and 2 iodides. Now, what you'll see, because the charge is +2, -1, +1, -1, charges are 2s and 1s, balancing numbers will also be 2s and 1s, okay? Now if I draw this as kind of a picture, right, and I've got 2 Ki, and then 1 PbNO3. Okay, so make sure you understand this, right? So PbNO3 twice means Pb stuck to 2 NO3s, right? 2 Ki's is a Ki and a Ki, right? 1 PbI2, Pb, 2 I's, I2. 2 KNO3, 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 2 of them. All right, so fair enough, we got that. Okay, we got that. Now, when I write my complete, I'm just basically splitting them into their ions if they're aqueous. Oh, I forgot to assign a state symbol. That's going to be aqueous because it's nitrate. Okay, we always start with solutions, so they're always aqueous. That must be the solid, but let's confirm. Iodides, lead's an exception, so it's solid. Okay, so lead 2 iodide is the solid. So this one stays intact, and all the others are aqueous, so they break apart, right? So a nice way to think about that, maybe I'll do some more origami, right? Oh. So the complete, when I look at it, okay, when I look at it, I'm going to have 1 Pb2 plus and 2 nitrates. So I'm going to have Pb2 plus aqueous and 2 nitrates. That's what I got when I split that one apart. And then 2 K pluses, 2 I minuses. Turns into, that stays intact, it's a solid. 2 K pluses, 2 NO3 minuses. Okay, so that's your complete. Okay, hopefully that makes sense, right? A little bit more complex because we have, you know, multiple passengers in the car, right? So think of this as a car with 3 passengers, 1 guy and 2 girls get out, right? Here we got 2 cars, each with 2 passengers, 2 guys and 2 girls get out, right? Okay, you got the idea. Now, once we got that, if you just want to cancel the spectators, you can do that. Or just think to yourself, what did I make? Lead iodide, how did I make it? Lead plus iodine, or iodide, right? So then I get Pb2 plus, careful, 2I minus, PbI2, solid. And there's a nice little picture of what actually happens. Okay, so it's kind of nice. All right, so practice those. Okay, practice those. We'll definitely have one of those maybe on the next quiz, definitely the next exam. Okay, now practice makes perfect. Okay, practice makes perfect. So what you got here, it says group task. It's just you. So balance, complete, net. Balance, complete, net. Balance, complete, net. Okay. Got 7 minutes left, so I think we've got plenty of time. Okay. So great place to pause. If you want to try these, try them, all right? Okay, but I'll go through them. Okay, so here you go. Silver nitrate, AgNO3. I know that's aqueous. The reactants are always aqueous because they have to be separate mobile ions to bump, right, and to react. Plus calcium hydroxide. Now careful, calcium hydroxide is +2 - 1. So when I swap partners, I get calcium nitrate. Calcium's a +2, nitrates are -1. That's going to be aqueous, right, because it's a nitrate. Plus, what's left? Silver hydroxide, +1 - 1. And hydroxides, if you remember, generally solids. We saw silver hydroxide earlier as an example, as a solid, right? Is it balanced? No. Okay, I got one silver, one calcium, one calcium. Oh, two hydroxides, two silvers, two nitrates. Oh, careful, see what I did there? +2, -1, need two of them. Okay, there we go. Let's just recap. Two AGs, two nitrates, one calcium, two hydroxides. All right, there it is. So that's my balanced. Complete, I've got to split these up. So that's AgNO3 twice. So that's 2Ag plus 2NO3 plus one calcium hydroxide. So that's one calcium, aqueous, right? One calcium, 2 plus, two hydroxide, aqueous. Turns into, that was an aqueous. Normally we'd switch the order. Traditionally you put the solid first. Now maybe I'll do that. 2AgOH solid plus one calcium and two nitrates. What cancels? Nitrates and calciums. What am I left with? Now, if you're looking at this before you did your exam, you're in luck. Okay? What's the definition of a balanced chemical equation? That is not the answer, right? It's the lowest whole number ratio. So make sure whenever you write your final balanced equation, be it on the quiz or this or wherever it is, it's the lowest whole number ratio. I was hoping you guys have picked that up doing the homework, all right? So, all right, so there we go. The answer is always the lowest whole number ratio. These are all lowest whole number ratios, okay? Next one, barium nitrate, +2 -1, need two of them. Plus sulfuric acid, hydrogen sulfate. Remember, acids are ionic when dissolved. Okay, so that's the H plus that's an electrolyte. That's the sour taste on your tongue, right? Turns into, well, we're going to get barium sulfate. We check our list, that's the solid. Plus H plus NO3 minus hydrogen nitrate, nitric acid. Nitrates are all aqueous. Let's count them up. 2 ions and 1. 2 H pluses, 2 H pluses. 1 barium, 1 barium. Looks good to me. All right. Now, anything aqueous we can split apart. 1 barium, 2 nitrates. 3 passengers in the car. 1 guy and 2 girls get out, right? Careful here. This is not a molecule. It's an aqueous acid, right? So that's 2 H pluses. Careful with acids, they're a little bit confusing. When dissolved, aqueous, they're ionic. This is a solid. 2 H pluses, 2 nitrates. What cancels? Nitrates and hydrogen ions, right? What do we make? Barium sulfate. How do we make it? Ba2 plus aqueous plus SO4, 2 minus aqueous. Makes barium sulfate solid. All right. Now, this last one, we used to do this lab years ago. We don't do it anymore, but it's a fantastic example, right? It's got lots of balancing numbers. So calcium chloride, CaCl2 aqueous, plus sodium phosphate, Na3PO4 aqueous. Swap partners in words, what am I going to get? Calcium phosphate, right? So that's a +2 and a -3. So that's a 3-2 situation. That's a solid, calcium phosphate's bone essentially, plus sodium chloride. Remember, names to formulas. It's not balanced yet, of course, because it's got the names to formulas. 1 calcium, 3 calciums, that was a 3 there. 3 chlorides now. Sorry, 3 calcium chlorides, 2 chlorides per formula units of 6 chlorides, 6 sodiums. 6 sodiums, 2 phosphates, 2 phosphates. That's it. Tricky, but there it is. Complete, I have to write small, it's a lot of stuff. So it's 3 calcium chloride, so that's 3 calcium, 6 chlorides, right? So 3 Ca2 plus aqueous plus 6 Cl minus aqueous. Here, 2 3s are 6, 6 Na plus aqueous plus 2 phosphates, because it's 2 vehicles with 1 passenger per vehicle for phosphates. Turns into the thing we just made, solid, plus NaCl breaks apart, 6 of them. 6 Na plus, 6 Cl minus. Those cancel. What am I left with? Calcium phosphate was my product. 3 calcium ions plus 2 phosphate ions. I made calcium phosphate. There we go. All right, so practice those. Talking of which, went right to the wire on the timer there, so just so you got everything in case it just cut off. Here's an old exam question, and then we kind of look on the back, there it is, okay. Then it says, list the names and formulas of 5 insoluble ionic compounds containing hydroxide ion. If you look at your solubility chart, hydroxides are generally solids, right? And it wants 5 insoluble, so just list any 5 that aren't exceptions, right? And it talks about that here. Okay. All right, so hopefully that's good. I'll get this up right now. So try and get this done before the end of the weekend. Again, look at this. Hopefully you've looked at this and it will help you if you need help with your concentration for your lab. Okay. See you next time.